Welcome back. In this block we leave solar cell technology based on inorganic semiconductor materials like amorphous and nanocrystalline silicon, cadmium telluride, CIGS and 3,5 semiconductor materials behind. We are going to look at organic solar cells like polymer cells. The learning objectives of this video are: how do energy levels form and thus carrier transport occur in organic molecules? What is an exciton? How is doping in organic PV different from inorganic PV? How does the fusion of excitons and charge separation occur through heterojunctions? And what is the typical architecture of a bulk heterojunction organic solar cell? Organic solar cells can be defined as solar cells containing an absorber material made of conductive organic polymers or organic molecules that are carbon-based, which may form a cyclic, an acyclic, a linear or a mixed compound structure. Due to the use of different absorber materials, these solar cells can be produced in a variety of colors, as you can see in the picture. A few examples of organic absorber materials used in these solar cells are PCBmC61 and P3HT and phthalocyan. In another example, benzene with an empirical formula of C6H6 has alternating double bonds in its structure, denoting the presence of free non-bonded p orbitals on neighboring carbon atoms. Intermixing of these empty pz orbitals results in the formation of delocalized p orbitals. This delocalization of p orbitals allows the free movement of charge carriers, thereby allowing carrier transport. The sideways intermixing of p orbitals can take place in two ways: constructively or destructively. The constructive intermixing of these orbitals gives rise to a stable bonding p state with a lower energy, and the destructive intermixing gives rise to an anti-bonding state, a pi state with a higher energy level. This splitting of molecular orbitals is what forms the band gap, the forbidden gap in such organic molecules. The lower energy state is preferred by electrons and is occupied under normal room temperature conditions. This state is hence termed as the highest unoccupied molecular orbital, or HOMO, and the higher energy state, which is the relatively unoccupied, is termed as the lowest unoccupied molecular orbital, the HUMO. These are analogous to the valence band and the conduction band in inorganic materials. This is how organic materials can showcase semiconductor-like properties. As you may know by now, in semiconductors the charge carriers consist of a negatively charged electron and a positively charged hole. Physically, though, a hole represents a pocket in the crystal lattice that is devoid of a negatively charged electron, that in turn gives it a positive charge. On being excited by an incident photon, an atom absorbs this energy and utilizes it to knock an electron in its valence band. The knocked off electron leaves behind a positive hole in the lattice, and due to this difference in charge, there's an inherent Coulombic force of attraction between electron and hole. In most inorganic semiconductors, however, this force of attraction between those two charges is very minimum, and due to this low binding energy, they can easily be split into independent charge carriers. In organic materials, however, the properties of the material causes an increased Coulombic force of attraction between the excited electron and hole. This high binding energy prevents the complete ejection of electrons on being excited with high energy photons. Thus, on illumination, complete charge separation does not take place, but an exciton containing both the electron and the hole is formed. The exciton can be imagined as a sphere containing the electron and the hole bound by mutual Coulombic forces of attraction. The splitting of electron and holes does not take place unless the exciton is subjected to a strong electric field. An important limitation posed by this exciton is the small diffusion length. The small diffusion length is a result of high recombination rates. Due to the stronger binding forces between hole and the electron, the likelihood of electron-hole recombination is very, very high. Under normal conditions, the diffusion length of these excitons is 1 to 20 nanometers. As you may recall, effective charge separation requires a p-n junction, which is obtained by different doping in inorganic semiconductors. However, there's also a known fact that doping increases the number of defects in the crystal lattice in semiconductors, which in turn increases the Shockley-Reed-Hall recombination. Thus, effectively, doping brings down the diffusion length of any said material. With an already low diffusion length due to the excitons in organic absorber materials, doping is generally not the preferred means to obtain a p-n junction. Hence, we use intrinsic materials. At this point, let us recall some definitions that will help us understand the concept of doping and charge separation in organic solar cells. As you already know, the energy band diagram gives a picture of the conduction and valence bands along with the band gap of a material. In addition to this, it also shows us the vacuum state. Electrons in a material are naturally bound with the surface of the material and cannot freely diffuse into the free space around it. This is due to a certain energy barrier that prevents the free diffusion of electrons into the free space. The vacuum level can be visualized as this energy barrier, making it the minimum energy possessed by an electron present outside the material. It can thus be defined as the energy of a free stationary electron that is outside any material. Ionization potential can be defined as the energy required to excite an electron from the valence band or the HUMO to the vacuum energy level. On the energy band diagram, this translates to the difference in the energy between the vacuum state and the valence or HOMO. Using this definition, we can infer that a material with a low ionization potential requires very little energy to excite an electron from its valence band to the vacuum state and hence can be called an electron donor. Electron affinity can be defined as the energy released while moving an electron from just outside the semiconductor of the conjugated polymer to the bottom of the conduction band. This can be represented on the energy band diagram as the difference in energy between the vacuum state and the conduction band or the LUMO. This means that a material with high electron affinity will very easily be able to attract an electron into its conduction band from the vacuum state and hence can be called an electron acceptor. Up to now we have discussed the basic properties of organic materials. In the next video we are going to make a solar cell based on these organic materials. So see you back in the next video.